Alrighty. Okay, so we left off here at section 10.7, allylic halogenation, and we discussed bond dissociation energies quite a bit today. We talked about the difference between a tertiary, secondary, primary, and methyl radical, but then we talked about allylic radicals, and we said those are even more stable than a tertiary. And so it says here, recall that the weakest carbon-hydrogen bond, the one with the lowest bond dissociation energy, is going to undergo radical hydrogen abstraction faster than the others, again, because we produce something that's a more stable radical. So alkenes will selectively undergo hydrogen abstraction at the allylic carbon. If you look at all the bond dissociation energies, you see that the bond dissociation energy that would produce a vinylic radical is the highest because you end up with a radical that is very unstable. You see that the green one is intermediate because you end up with a secondary radical here, which is not unstable, but it's not nearly as stabilized as if you were to pull off the allylic hydrogen, the one that's highlighted in blue, you would end up with a resonance stabilized radical, wouldn't you? You end up with an allylic radical, and you can draw the resonance contributor of that just by putting in the fishhook arrows like this, okay? And so, again, if we take an alkene and we subject it to halogenation conditions, we're going to get halogenation occurring at the allylic position. So hydrogen abstraction of an allylic hydrogen generates that resonance stabilized allylic radical. We just talked about that. And so if you take an alkene like cyclohexene and you treat it with bromine and you subject it to electromagnetic radiation, you end up with bromination occurring at the allylic position. But you all know enough that if you take an alkene and you subject it to enough bromine, Br2, what's going to happen? You're going to do a halogenation reaction, aren't you? And you would end up with anti-addition to produce the trans 1,2-dibromo cyclohexane, okay? Plus you'd end up with its enantiomer. So how do we avoid this competing reaction that's occurring right there? How do we avoid that? Well, organic chemists have developed a way to avoid that reaction that I had in red from occurring. And the way that we avoid the competing alkene addition is that we use NBS, which is N-bromosuccinimide. We use that as our source of bromine radicals instead of using bromine, and that way we keep the amount of bromine in our reaction mixture, or Br2, we keep the amount low. So it says down here that when you take NBS and you subject it to light, that this bond, this nitrogen-bromine bond, is actually pretty weak, and it ends up breaking to give you a resonance-stabilized radical. So this is resonance-stabilized, and you could draw both of the resonance contributors for that, and we produce a bromine radical. Well, what that bromine radical is going to do is that when it comes into contact with NBS, is that it reacts via an ionic mechanism to produce Br2, okay? So what happens? It says that the NBS keeps the concentration of HBr and Br2 low, so the competing addition reactions of the alkene are minimized, so that we get allylic bromination occurring preferentially. So let's take a look. It says propagation. Using the bromine radical, we do the hydrogen abstraction to produce our allylic radical. But again, the HBr that we produce here, that reacts with NBS in an ionic mechanism, which isn't even in our textbook, to form bromine, and then that bromine continues the propagation to do the allylic bromination. Okay, so what's the take-home message for you as an Organic Chemistry 1 student? Is that if you take the alkene, okay, and you treat it with NBS, where is it? Where's my reaction? Let me just, if you want to do this reaction here, okay, that your best conditions for doing that would be to treat it with NBS and light, okay? So we'll say NBS and light are preferred. Preferred reaction conditions. Now, of course, it does proceed through a radical. Okay, we see that we end up producing an allylic radical. So what would happen if you had an asymmetric alkene like this one here? This is 3-methyl-1-butene. If you treat that with NBS and light, you end up producing the allylic radical. Where's the allylic hydrogen? It's this one here. So you end up producing this radical. Okay, but you know that that radical is going to undergo halogen abstraction to make this product, but it can also have a resonance contributor, which is going to be this. Let's draw it out. It's going to look like this, okay? A primary allylic radical, which is going to undergo halogen abstraction to produce this regioisomer. So we end up with a mixture of isomers in this case. And here are the two radicals drawn down here. And so you should be able to determine that when you do an allylic bromination, since you form a radical as an intermediate, that can, if that has a resonance contributor that is not the same in structure, you're going to end up with a mixture of regioisomers. So with all that in mind, let's predict what happens when each of the following compounds is treated with NBS. So NBS and irradiated with ultraviolet light. Well, there's only one type of allylic proton in this first alkene, in B, isn't there? This is an allylic position, but there's no hydrogens here. This is also an allylic position, and there are 3 hydrogens there. So we're going to abstract this hydrogen that I'm writing in red right now. We're going to end up with this intermediate. Let's write it out. So we're going to end up with this intermediate. Okay, but that radical does have a resonance contributor, and we could draw that. Okay, son of a gun. Keep doing that. There we go. We could draw that resonance contributor. So let's draw it out. But that's going to be this. Could anybody tell me what the relationship is between these two compounds, or these two resonance contributors, I should say, in the yellow box? What would be the relationship between these two? They're identical. Exactly. Thanks, Mackenzie. They're 100% the same. And so I'm going to delete the second one since it's the same as the first, right? So we're going to just have that as our only intermediate. Okay, and then that's going to undergo the halogen abstraction to make this compound. So you just get the allylic bromination occurring. And that's it. All right, if we take a look at the next one, you can see that there's an axis of rotational symmetry in the molecule. So this allylic hydrogen and this allylic hydrogen are chemically equivalent. They're both identical, again, in terms of their equivalency. But if we just abstract one of them, so let's just take this one here, okay? If we rip that off, what do we end up with? Let me draw it in blue here. We end up with this. There we go. We end up with this radical, which does have a resonance contributor. So here's our allylic radical. So let's draw what that looks like. And it's going to look like this. Make sure I don't mess it up. There we go. So we end up with these two resonance contributors, which are not identical. I can make this one a little prettier. Here we go. Like that. And both of these resonance contributors can undergo a halogen abstraction. So let's pencil that in. And then you're going to end up with two different products, aren't you? So you're going to end up with this compound, which has no stereocenter. And then you're going to end up with this compound, which does have a stereocenter. This one here, right? This is a stereocenter right here. And so you end up with a pair of enantiomers here. So I'll put plus enantiomer. There you go. So you end up with a mixture of 3 compounds for the second one. All right. Well, the last thing I want to talk to you about today is the radical addition of HBr across a double bond, right? We talked about this at length in the alkenes chapter, and we said, okay, well, if you add HBr across a double bond, it proceeds with Markovnikov regioselectivity, right? Because you do the protonation, you end up with the most stable carbocation, right? The rich get richer, then the bromide comes in as a nucleophile, you do the nucleophilic attack, and you end up with that compound. Okay, great. Well, we also saw that if you treat it with HBr and you have an organic peroxide in there, that you get anti-Markovnikov addition. Well, there's a good reason why we get anti-Markovnikov addition, and you have to have a little bit of knowledge of radicals in order to understand that. Well, we saw earlier on today that an organic peroxide is a radical initiator. So what's the first step of the mechanism going to be? Initiation, right? We take that radical initiator, that organic peroxide, we heat it up, and it makes 2 alkoxy radicals that you can see here. Then that's going to react with the HBr, in our reaction mixture to make a bromine radical. So the 2 steps in the initiation here, okay? Everything that we've looked at until today only had 1 step, but today, or sorry, in this one, it's got 2 steps. So the first step is the organic peroxide breaking apart to make a radical. Then that reacts with HBr, but the end result is that we end up with a bromine radical. So here's the key step that helps us understand why we get anti-Markovnikov addition. It's because of the radical addition to the double bond. Check it out. The radical can add either to the less substituted carbon, like this, to give us the more substituted radical, which is going to be the more favored radical, or it could do this. It could react on the more substituted carbon to give us the more unsubstituted or the less stable radical. Now, which one of these is going to predominate? Obviously, it's the one that's favored, right? So when we did hydrohalogenation back here, what was the first step? It was a proton transfer, and we ended up with the most stable carbocation. Well, now the first step isn't the addition of the hydrogen. The first step is the addition of the bromine, and we want to get the most stable radical. So again, when we did the hydrohalogenation, the proton transfer was the first step. We got the most stable carbocation. But now this pathway, the addition of the halogen, is first, okay, producing the most stable radical. So it's going to add to the side that produces the more stable carbon radical, as that's going to be a lower energy intermediate and therefore a lower energy transition state for our addition to our pi bond. If we take a look at the 2 steps, okay, the addition to the pi bond followed by the hydrogen abstraction. Again, you see that the bromine adds to the less substituted carbon to produce the more stable radical, okay? Then the carbon radical abstracts the hydrogen from HBr to make the product, and look what you end up with. The bromine radical, and just the chain reaction will just keep going. And so what's termination? Any 2 radicals coming together. And if you're like, well, couldn't I draw 2 other radicals that you had previously? Yep. Just draw those coming together, and that, my friends, will always count as a termination. It even says it right here. The combination of any 2 radicals will constitute a termination step. Well, I told you that this anti-Markovnikov process, right, this process right here, I told you that it only works with HBr. It doesn't work with HCl, doesn't work with HI. Well, we go over here. I have a comment about that. It says the anti-Markovnikov radical addition of HBr is generally spontaneous, whereas the radical addition of HCl and HI are generally non-spontaneous. Well, if we go back here, we see that there's 2 propagation steps, right? There's the addition step, and there's the hydrogen abstraction step. If you look at the change in Gibbs free energy for those 2 steps, so the first step is the radical addition. So put in radical addition. The second step is the hydrogen abstraction. So we'll put here hydrogen abstraction. And we compare them for doing the reaction with HCl, HBr, and HI. Check this out. If you look at the change in Gibbs free energy for all of these processes, okay, and I probably didn't give myself enough room here, but the radical addition with HCl is actually a spontaneous process. The delta G is negative. And the same thing occurs with HBr. The delta G here is also negative. The first step, the radical addition with either the chlorine radical or the bromine radical. They're both spontaneous at low temperature, both of them. Whereas if you look at the radical addition with HI, it's actually an endergonic process. So the delta G is positive, and therefore that's going to put the kibosh to the whole thing. That renders the reaction non-spontaneous. Well, if you look at the halogen abstraction, what you see is that when you have the radical that's formed from chlorination, the second step, the delta G is positive. And again, that puts the kibosh to the whole thing too. So both of these processes are going to be non-spontaneous. Whereas if you look at the hydrogen abstraction with HBr, we end up with our delta G being negative here as well. The delta G here is negative too, but again, this one ruins it. So since both the hydrohalogenation using radical conditions with HCl and HI, they're both non-spontaneous because one of the steps has a positive delta G. It's just non-spontaneous. Whereas when we want to use HBr, both steps are spontaneous. And that's why we can do the radical addition with HBr in an anti-Markovnikov fashion, but we can't do it with HI and HCl. Now, in terms of stereochemistry, well, it says that recall that addition reactions often form a new chirality center. Now we know that we have the bromine radical, right? That's going to add to form the most stable radical. So let's draw some fishhook arrows here. Okay, you would actually end up with this intermediate. Son of a gun. You would, nope. I lost an arrow somehow. Let's pencil it back in. Okay, so you'd end up with this intermediate. I'll try to draw it as neatly as I can. You would end up with this intermediate here. Okay. Now, in this case, after the hydrogen abstraction, you don't form a chirality center, so you don't have to take that into consideration here. However, if the substrate is not chiral, again, then you get a racemic mixture formed. But if the starting alkene contains a stereocenter, just like I told you before, if you can form a mixture of diastereomers, you're not going to form them in a 50-50 mixture, right? Because the last step is going to be affected by that chirality center. Well, with all that in mind, let's take a look at one more problem. It says predict the products for each reaction. In each case, be sure to consider whether a chirality center is being generated. Then draw all expected stereoisomers. So what's going to happen? We're doing anti-Markovnikov addition of HBr across the double bond in both cases. Now, all of you could draw the products of this. I know you could, okay? Because we've looked at this already. But let's consider the mechanism a little bit. We have our bromine radical. It's going to add to the less substituted carbon to form the more stable radical. So let's draw the radical that's formed. And this is the radical right here. And so now, when you do the hydrogen abstraction in the next step, it can occur from either face of the molecule. And so you can end up with this compound where you have the methyl group going up, or you could end up with the enantiomer where you have the methyl group going down. So we end up with a mixture of enantiomers in this case. So these are enantiomers. In the next one, I have my bromine radical. Let's draw it out. Let's try some curved arrows here. Okay, I'm going to add to the less substituted carbon to form the most stable radical. Okay, and this has no stereocenters, right? After I do the hydrogen abstraction here, I end up with this compound over here, which has no stereocenters. So no chiral centers to even take into consideration here whatsoever. And so what we're going to do next class is we're going to cover section 10.13. I want you to take a look at it yourself. And as I showed you earlier on today, chlorination is really only useful when you have a highly symmetric substrate, whereas bromination is slower, but it's more selective. And so if we needed to move the bromine around the molecule, we could do that using elimination, producing the Zaitsev or the Hoffman alkene, depending on what we want to do. And so the real advantage of halogenation is functionalizing an unreactive alkane, right? You start with something that has no functional groups, right? An alkane is not a functional group. And now you convert it into an alkyl halide, and now you can do stuff, right? You can do a substitution or an elimination. Can anybody identify what this picture represents? Does anybody recognize this character?
Is it Pandora's box?
Hell yeah, it's Pandora's box. Yeah, so you can tell that I pasted that in there, but that's what it represents. It's Pandora's box. Like literally, you guys, you know, if you give an organic chemist an alkane, there's not much you can do with it. So that is good news, because anytime you see an alkane in a synthetic problem, all you can do is brominate it, pretty much, or chlorinate it, right? But then after you do, you know, once you have a haloalkane, I mean, then the world is your oyster, baby, right? And once you make an alkene, I mean, think about it. You can do so many different things. Let's say you made an alcohol, right? You just did a solvolysis. Well, you can do lots of stuff with an alcohol too. Then we'll see in organic chemistry too. But the idea is that we're really busting the doors open now to so many different possibilities. So to review all the reactions that we learned, here they are, okay? This is all the reactions that we covered. And this one you had already learned. Anti-Markovnikov addition of HBr across an alkene, but now you understand why, right? You understand that the bromine radical adds to the double bond first to produce the most stable radical, followed by a hydrogen abstraction. We talked about allylic bromination and how we mitigate addition to that double bond by using N-bromosuccinimide and heat that keeps the concentration of bromine and HBr low. And then we talked about the bromination of an alkane, which is regioselective for the most substituted carbon because it's going to produce the most stable radical. And that is all of the content of chapter 10.